Welcome to the lecture on 6.1 for power series. So to start, it's going to look similar to the infinite series we were just working with, except we're bringing back that variable x. So in general, the form for a power series is what you would expect. It's c sub n, which is our coefficient, times x to the power n. So it's basically just an infinite polynomial. We could also kind of shift it horizontally. So if we take, instead of x to the n, x minus a to the n, then that just represents a horizontal shift by a. But in general, this is what we've seen in the past infinite series, a little bit of a different summation because we're starting at 0. I think typically in the last chapter we started at 1 a lot, but think about this: if we have powers of x, in order to get a constant term, we need to raise x to the 0th power. So starting it at 0 will allow us to have a constant term and then successive powers of x. So if we want to talk about the convergence of the power series, then the most obvious thing would be that if I plug in a for x, then x minus a becomes 0. And so this would make sense that it always converges at its center. So a is called the center. So if x equals a, then our series would be n equals 0 to infinity of c sub n a minus a to the nth power. So the summand becomes 0, which adding up a bunch of zeros forever is just 0, right? So that's kind of a trivial case. The other cases could be that the series converges for all real numbers x. So it doesn't matter where x is, this thing will always converge. And then the last situation would be that we have a radius of convergence. So capital R stands for the radius of convergence, and we saw that at the end of chapter 5. In chapter 5, everything was centered at 0. So now we're just going to look at it as a little bit of a shift. So let's talk about radius of convergence and interval of convergence. So this is the first, if we just look at theorem 6.1. Right, so the first figure here represents that the series converges only at A. So there's just one point where this series will converge. In the second figure, we said that it would converge for all real numbers x. And then in the third case, we said that it would converge on a certain interval about x. So going back to the first figure, the radius of convergence is 0, and the interval of convergence is just a single point, A. So when I have curly braces around one number that I've listed, it just means that it does it for only one point. In the second figure, our radius, we just denote it as infinity. And our interval, even though we're centered at A, it doesn't matter because I'm going to go from negative infinity to positive infinity. And then for the third figure where we have some finite radius and we're centered at A, the radius equals capital R, right? So the distance from here to here, this is R, and the distance from here to here is also R. So then our interval would be a minus r to a plus r. So I can be as much as r distance away from my center, which is a. It may be the case that we'll have a closed interval, or maybe it's just closed on one side. So let's look at some examples of that. All right, so we have our power series here, and we want to find the interval and the radius. So remember that radius is a number, a single number, and our interval is going to be a set. So when we're talking about the convergence of a series, we're going to fall back onto all the tests that we learned in chapter 5. So if I wanted to consider this series here, I would apply, because I have the factorial, I would think, okay, maybe I'll apply the ratio test. But then I also have x to the n in my numerator. So I'm like, oh, maybe I should apply the root test. And what helps me pick between the two is that taking the nth root of n factorial sounds very messy and something that I wouldn't want to do. So I'm going to apply the ratio test. So just remember that the ratio test says that if 0 is less than or equal to rho less than 1, we get absolute convergence. If rho equals 1, it's inconclusive. And if rho is greater than 1, then it's going to diverge. So let's set up our ratio. I take the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial. That's the n plus 1th term. And then take that over the nth term, which is x to the n over n factorial. And of course, all of our n's are 0 or greater. So the only thing that really we need to be careful about in terms of absolute value is x. So I'm going to simplify and keep my absolute values in place for now. So I get x to the n plus 1 over x to the n times n factorial over n plus 1 factorial. And so this further simplifies to absolute value of x over n plus 1. And again, since n is non-negative, what I'll end up with is the limit as n goes to infinity of just the absolute value of x over n plus 1. So if I can get this limit to be less than 1, I'll know that it's absolutely convergent, and then I'll kind of base my assessment and my interval and my radius on that. So notice that x is not dealing with any powers of n here. So in effect, it is a constant with respect to n. So I can pull it outside of the limit. And the limit as n goes to infinity of 1 over n plus 1 is 0. So this is absolute value of x times 0, which is 0. So regardless of x, rho equals 0, right? So there's no x value I can put into this ratio that's going to make the limit not be 0, which means x can be anything it wants. So x can be anything, and the mathematical way of expressing that is that our radius of convergence is infinity, and our interval of convergence is negative infinity to positive infinity. So now let's look at B. The book solves it in one way, and I actually, well, I would just consider another approach. I think they're both worth looking at, so please check out the text when you can. Okay, so our series is n factorial over x times x to the n. So n factorial is just going to blow up as n increases. So for me, I'm thinking like, there's just no way that this thing can converge, except for in one small case. So let me see if I can move all this stuff down really quick. So let's consider two cases. The first case if x is 0. And the second case will be x is not 0, right? And so that takes care of all possible values of x. You're either 0 or you're not. So if x is 0, then what we get is n equals 0 to infinity of n factorial times 0 to the n. So this just makes the summand equal to 0. So I get the sum of 0, n equals 0 to infinity, which equals 0. So this converges. So we know that it converges at x equals 0. If x isn't 0, then if we apply the divergence test, the limit as n goes to infinity of n factorial times something that's not 0. It doesn't matter how small x is, this thing is not going to, the limit will not be 0. So it diverges. So when you have this equal sign arrow combo, that means implies for a conditional statement if then. So if the limit is not equal to 0, then the series diverges, is what this notation means. So for us, it's just going to converge at one point. So our radius equals 0, and our interval of convergence is just a singleton, the point 0. It's the only place where it will converge is when x is exactly 0. And then for our last example, C, we have the series n equals 0 to infinity, x minus 2 to the n, over n plus 1 times 3 to the n. And this is interesting because it differs from A and B in that it's no longer centered at 0. So just scroll up to the examples really quickly. So this one is centered at x equals 0, right? This one is also centered at x equals 0. And this one is centered at x equals 2. All right, so for this one, I'm going to apply the root test because everything's raised to the nth power, more or less. So it's the same deal with rho for the root test as well. Oh, I think I forgot to mention something really quickly. Sorry. No, okay. All right, so I'm going to apply the root test. So I'm going to take the limit as n goes to infinity of the nth root of the absolute value of x minus 2 to the n over n plus 1 times 3 to the n. So I'll get a cancellation of everything raised to the nth power. And what I'm left with is the absolute value of x minus 2 over n plus 1 to the 1nth times 3. And again, x minus 2 is not affected by n, and neither is 3. So what I'm going to do here is I'm going to pull out x minus 2 and 3. If either of those had an n anywhere playing on it, I couldn't do this. But since they're completely isolated from n, I can flip them outside of the limit as constants. So I get x minus 2 over 3 times the limit as n goes to infinity of 1 over n plus 1 to the 1 over n. And I can also rewrite this because 1 is on top, it won't be affected by applying an exponent to it. And so as n goes to infinity, this is going to bring us to a 0 to the 0th. So in order to take this limit, I'm going to have to do that fancy log L'Hopital combo. So we'll let the limit as n goes to infinity of 1 over n plus 1 to the 1 over n. We'll suppose that it equals L. And then so I get the log of the limit equals the log of L. So this, I can flip the natural log inside the limit. So I get the limit as n goes to infinity of the natural log of 1 over n plus 1 to the 1 over n equals the natural log of L. I still don't have enough space. Okay. So next step, limit n goes to infinity of 1 over n times the natural log. Actually, I'll just write this in one fell swoop. So this is going to be ln of 1 over n plus 1 over n. And as n goes to infinity, this will go to negative infinity over infinity. Definitely need those parentheses. So this will go to negative infinity over infinity. So I can apply L'Hopital's rule and take the derivative. And so this is how I take the derivative of ln of 1 over n plus 1. I think it's a little bit easier. This is really just ln of 1 minus ln of n plus 1. So if I take the derivative, then it becomes minus 1 over n plus 1. And so that's the derivative of the top. And then the derivative of the bottom is just 1. So I end up getting -1 over n plus 1. And then this is just 0. So we have that 0 equals ln of L. So e to the 0, which is 1, equals L. So back to our original. So I'll take this, and that is going to become our limit here. So this equals x minus 2 over 3. And remember, so this is rho, right? Our limit. So if we have then 3 cases, I'll write down here. My spatial planning was not great on this one. So our first one is that rho, which equals the absolute value of x minus 2 over 3. If this is less than 1, then we get absolute convergence. So we just need to solve this inequality. And we get the absolute value of x minus 2 is less than 3. So we should end up with -1 less than x less than 5. So what's interesting to note here is that this is our radius, and this is our interval. We also know that if x minus 2 over 3 is greater than 1, then we get divergence. So anything outside of -1 to 5, like here's kind of what we've constructed so far. So we're centered at 2. Then we have 5 and -1. So I know that I'm going to, from here to here, I'm going to converge. And I know I'm going to diverge over here. But what I haven't determined yet is whether or not I converge or diverge at these endpoints. So like right at the point. I haven't made an assessment right at the point. So the next thing I'm going to do is I'm just going to test at the points -1 and -5. So at x equals -1 and x equals 5, rho is equal to 1, which is inconclusive. So we have to test those individually. So at x equals -1, our series would be n equals 0 to infinity. Of -3 to the n, right? So I'm just plugging -1 in for x. So I get -3 to the n over n plus 1 times 3 to the n. And if I simplify this, I'm going to get n equals 0 to infinity of -1 to the n over n plus 1. And this is an alternating harmonic series, which we know that this converges. it's a conditional convergence, but this converges. So this is an alternating harmonic, and so it converges. So that was at -1. So this guy converges. And now we're going to test at x equals -5, or x equals 5. So when I plug in 5 for x, what happens is I get, what do I get? 3 to the n over n plus 1 times 3 to the n. And this simplifies to n equals 0 to infinity of 1 over n plus 1. And so this is just your regular harmonic, which we know is a divergent P series with P equals 1. So now we've tested everything. And what we can say then, our radius is still 3. But our interval is going to now include -1, but it will not include +5. So we're going to write it like that. So we just added one more point to our interval where it's going to converge. So the moral of the story is when you get a finite radius of convergence using the root or the ratio test, because those tests are inconclusive when rho is equal to 1, you need to figure out what makes rho equal 1 and then test specifically at those values. All right, so why do we like power series? Well, in general, we like polynomials. And a power series you can think of as an infinite polynomial. We like polynomials because they're, first of all, they're really good approximations for otherwise kind of hard to work with functions. They're super easy to differentiate. They're really easy to add together. And they have all sorts of nice properties. Like I always think, and I think other people feel this way too, that polynomials behave a lot like regular numbers. Meaning like you can divide them, you can multiply them, you can add, you can subtract them, you can make a ratio of them. You can do a factorization. So, you know, we can always write a number in its prime factorization. Well, we can do the same thing with polynomials. We can always write it as a product of its factors. So fundamental theorem of arithmetic directly relating to the fundamental theorem of algebra, wherein we go from integers to polynomials, but it all acts the same anyway. Soapbox rant over. So representing functions as power series, we want to do it because polynomials are nice. That's the short answer. And remember in chapter 5 that we have, let's see, we worked a lot with geometric series. So we said that n equals 1 to infinity of a r to the n minus 1. This was equal to 1 over 1 minus r, and it converges when r is strictly less than 1, and it diverges when the absolute value of r is greater than or equal to 1. So here we don't have any sort of inconclusive type stuff happening at 1. If r equals 1, it diverges, just period. So we don't have to worry about testing endpoints for the geometric series. I did mention in, I want to say it was lecture 5.2, I can also write this as n equals 0 to infinity of a times r to the n. And these are the same. If you wrote it out term by term, you would see that they're exactly the same. I'm just switching the indices a little bit. So them being equal term by term means that this is also the case here, right? So these are the same. So same series, just a different starting point, and then I kind of compensate for starting at 0 by raising the power of the summand up by 1. Okay, so we're definitely going to use the geometric series here, and we're going to write these functions as a power series. So for A, f of x being 1 over 1 plus x cubed. So now we're going to get creative, and we're going to use subtraction 2 times to make addition. So 2 wrongs do make a right. 1 minus negative x cubed. Right, so we can see that these are exactly the same. And now I'm in the form for a geometric series. So instead of going from the series to the closed form for the geo, I'm going to start with the closed form and then express it as a summation. So I know that this is n equals 0 to infinity of a, which is 1, times r, which is negative x cubed, to the n. So this is a, this is r, oh, you know what? I made a boo-boo. These are a. Sorry about that. Okay, so now that I have it as a power series, and I also have it in the form of a geometric series to boot, I can say when this thing will converge. So now I want to talk about converges. So this is a geo series with r equal to negative x cubed. So it converges whenever the absolute value of negative x cubed is strictly less than 1. So I'm going to get negative 1 less than negative x cubed less than 1. So if I solve this, okay, so if I divide out by the negative, I'm just going to switch the signs and also switch, like it would be like this. Which is fine. Okay, then I'm going to take the cube root of everything. And so I just get 1x negative 1. So again, here, this is my radius. And this is my interval. Right, we're centered at 0 again, so this is pretty straightforward as far as like radius and interval, they almost feel the same. So our interval is from, I could also rewrite it as negative 1 to 1. And again, I don't have to check the endpoints like I did before, because I know that geometric series diverge when the ratio little r is equal to 1. So I don't have that, oh, it's inconclusive when it's 1. No. Geometric series either converge or diverge, period. It's like cut and dry, which is why they're fabulous. Also, they're super easy to differentiate. Okay, so let's try B. It's a little bit trickier. And then I'm going to add an extra example to show you when it's not centered at 0. So if I have f of x equaling x squared over 4 minus x squared, I need to get this a over 1 minus r, right? That's the idea. How do I get it to look like this? So the first thing I want to do is, I know I need a 1 where that 4 is. So the easiest thing I can do here is just factor out a 4. So x squared over 4 minus x squared. This is just x squared over, if I factor out a 4, I'll get 1 minus x squared over 4. That was pretty easy. And I'm just going to scooch the 4 up top. So this is x squared over 4 over 1 minus x squared. So now I'm in good shape because this is my A and this is my R. So we're good there. And now we can go ahead and push it into the sum. So if I want to write f of x as a power series, it really equals, so again, it was x squared over 4 minus x squared, but writing it as a power series, I can write it as n equals 0 to infinity of a, which was x squared over 4, times, oh, I lost my 4. Dang it, sorry about that. That's 2. X squared over 4 to the n, right? So this is expressing this right here. If someone said, hey, can you write f of x as a power series? This is your answer, right? That's writing, and you can simplify that a little bit, sure, but this is the power series that represents f of x. So now to compute the radius of convergence in the interval, for a geoseries, again, we just need the absolute value of r is less than 1. And our r, O-U-R, little r, our r, is x squared over 4. The absolute value of this has to be less than 1. So I'm just going to multiply through by 4. So by the way, this is already positive because it's squared. So I get this. So then I get x squared has to be less than or equal to 4. And the way that that happens is that negative 2 is less than or equal to x is less than, is strictly less, oh my gosh, tongue-tied again. Negative 2, strictly less than x, strictly less than positive 2. So our interval of convergence is negative 2 to positive 2. Again, I don't have to check the endpoints because when little r is equal to negative 1 or positive 1, it's going to diverge. So there's no ambiguity there. All right, so let's try one more example where we're not centered at 0, but I still want it to be a geometric series. So this is not in the book. So let's say I have 1 over, this one's pretty straightforward, 1 over 2 minus x. And I want to write this as a power series. So I need to get this in the form of a over 1 minus r. So the way that I do that is I know that 2 has to become, oh, there's 2 ways I could do this. Interesting. All right, well, you could do it in the way that we had above. I'm going to show you this other way that I think is kind of cool. Okay, so this equals 1 over 1 minus x minus 1. Right? So if I simplified the denominator, I would have 2 minus x. And so this is just kind of like another flavor of manipulating your expression into something that looks like a geometric series. So then for me, I know that a is 1, r is x minus 1, and voila. So in order to determine where this geometric series converges or diverges, again, I just set up my x minus 1, my little r has to be less than 1. So I get -1 less than x minus 1 less than +1. And so adding 1 to both sides, 0 less than x less than 2. So our interval of convergence would be 0 to 2. So we could do it in the way that we just did in example B. So just like for my own entertainment, I guess, let's just try alternative. That's supposed to say x over 2. Not doing a very good job. Okay, so now we're in business. So this equals 1/2 over 1 minus x squared. Okay, so a is 1/2 and little r is x over 2. So I get n equals 0 to infinity of 1/2 times x over 2 to the n then I have that x over 2 has to be less than or 1, and then I get -1 less than x over 2 less than +1. So then I get -2x 2. So what is the difference?